All right, so to help us out with our free body diagram practice, I wanted to go over a few helpful tips, such as what are the types of forces we could be looking at in class, and then how exactly do I draw a free body diagram with said forces. So there are 6 types that we'll be dealing with this semester. There are obviously more types of forces in this, but these are the only 6 we need to know for now. The first one, the most obvious and what we probably know, is everything experiences a force of gravity. And on a free body diagram, we're going to label that Fg. Another type of force is we can have a force of friction that usually slows objects down. Air resistance is technically a type of friction, so it falls under that category. Another type could be an applied force. This would be if a human is actually pushing or pulling with their hand. So that'd be Fa for force applied. If there's a spring in the problem, there also is a such thing as a spring force. If I have a rope, a cable, a string, a chain, or anything like that present in the problem, that could have a force of tension. That's the force inside whatever that rope, string, chain is. So that'll be F sub T. And then there's also, lastly, something called the normal force. So I want to cover what the normal force exactly is as I'm covering a free body diagram. So let's say I have my coffee cup resting on the table. How would I draw a free body diagram diagramming the forces acting on my coffee cup? Well, a free body diagram is obviously a diagram, so I'm going to draw some arrows because forces have direction. So forces can point in different directions, and they can also have different magnitudes. So that would determine how long I draw my arrow for each force. But this free body part, why do we call it a free body diagram? We call it that because I want to operate in such a way that if I'm pushing my coffee cup to the right, I don't want it to matter where I push the coffee cup. I want it all to have the same effect. Now in real life, if my coffee cup is pretty tall, if I push it up here at the top, that's going to have a different effect on the cup than it would be if I push at the bottom. Maybe if I push at the bottom, this cup just slides to the right on the table. But maybe if it's tall enough, if I push at the very top, this coffee cup would tip instead. So we're not going to talk about anything rotating like that this year. We're assuming that if I'm exerting a force, it is causing it to move in a certain direction but not rotate. So if I want to free ourselves from the body or the shape of the object, no matter what the object is, we're going to represent it as a dot. So the coffee cup boils down to a dot. If I was talking about a person, the person becomes a dot. Table becomes a dot. No matter what it is, we're going to represent it as that dot. And we'll talk about exactly what that dot stands for probably next semester. So let's go through these forces. Do I have the force of gravity acting on this cup? Well, if it's on Earth or any planet or the moon that has gravity, there's always a force of gravity that points down. That should probably be the first arrow you draw in every free body diagram. There's always gravity. Let's erase some of this for a second. Let's say my cup is just sitting here. I'm not exerting a force on it. If my cup is just sitting there on the table, does friction need to be involved? Well, if it's just sitting there and there's nothing trying to move it, then there is no friction, because friction wouldn't have to stop it from moving or slow it down if it was moving. If it's just sitting there, I'm not applying a force to it with my hand. I don't see a spring in this problem. I don't see a rope or a string. And the last one is a normal force. So there is a normal force present here, but why does there need to be? Well, think about this. If I've got my coffee cup on my table and the only force I see is the force of gravity, what would I expect my cup to do if there's only one force and it's down? What I would expect is my coffee cup would then fall because there's nothing balancing out this force of gravity. Think about a tug of war. If only one side is pulling the rope's not going to stand still. The rope's going to move towards the team that's pulling it. So if this coffee cup is sitting still, not moving whatsoever, there needs to be a force that balances out this force of gravity. And in this particular case, it is a normal force. The normal force is the table pushing back on the cup. So gravity pushes the cup onto the table, but the table has to push back to keep it at rest. So these forces are balanced. And that's all we're talking about this week, is when these forces are balanced. So, about to get into the practice, but before we do that, let's talk about some questions we can ask ourselves to determine, is each type of force present in the problem? Use a different color. So for the force of gravity, we're going to ask ourselves, is it on a planet or moon? 99% of the time, unless I say it's in outer space, there will be force of gravity. So for force of friction, ask yourself, is it sliding on a surface or being kept from sliding? So is it sliding, or is something pushing it and it's not moving because friction is preventing that from happening? So if that's the case, if you can answer yes to either one of those questions, you might have friction. For an applied force, ask yourself, for your object, is a human actually touching it? Is a human physically with their hand or foot or whatever pushing or pulling the object? If so, you may have an applied force. For spring force, this one's pretty simple. Is there a spring? For spring force, you kind of have to have a spring. For tension, we're going to ask ourselves, is there a rope, string, or anything like that in the problem? If so, and that rope is actually pulling on the object, you're probably going to have a tension force. And then for normal force, is it pushed against a surface? If it is, the surface has to push back with a normal force. So let's talk about one more case of the normal force. That's different than what I said before. So normal force for something on a flat surface always points up. And it points up because in math, the word normal means perpendicular. So this force has to be perpendicular to the surface. Well, what if I take and I'm pushing a book against the wall? So I push the book into the wall with an applied force. For that book to stay at rest, the forces need to be balanced. I can't just have the applied force and nothing else. If I push it against the wall is my surface now, and that has to push with a normal force that is perpendicular to the wall. That would be out in this direction. So depending on the orientation of your problem, the direction of the normal force can and will change. But in most cases, if it's on a flat surface, a horizontal surface, the normal force points up. Let's look at some of our practice. Okay, so let's quickly go through this. On this free body diagram matching, we have 9 options for free body diagrams, and they're listed A through J at the top. I've got 15 problems. Each one of those problems uses one of these free body diagrams. So it's a promise that some will be used more than once. So what I want us to do is, for each problem, draw the free body diagram. Don't just write the letter, actually draw it, and then label what those forces are on your diagram. So the labels are not here in the examples that we're choosing from, but I want to then list what types of forces are those arrows representing. So, ask ourselves some questions, the questions we just talked about with my types of forces to be able to tell if it's present. Let's look at number 1. The ball is being thrown in the air. The lines tell me it's moving up. So what we're going to find out is, for right now, for a free body diagram, the way it's moving has no effect on my free body diagram. I'm looking at forces, not velocity. So ask ourselves some questions. Is that ball on or near a planet? Yes. So that ball has a force of gravity acting on it. Is it sliding or being kept from sliding? No, so there's no friction. Is a human physically touching it at this moment? No, this guy's standing over here scratching his head. Is there a spring? No. Is there a rope? No. And then finally, the last one. Is it being pushed against a surface? No. So the only question I answered yes to was gravity. So that's the only force I put on my free body diagram. You're going to be tempted to draw a force up because it's moving up. But just because it's moving up does not mean there's actually a force on it at this moment causing it to move up. So it's only the force of gravity. This may seem out of order, but let's look at number 9. Number 9, kind of the same problem, except it's just moving a different way. It's being thrown to the right and up instead of just up. We'll ask ourselves, is it on a planet? Yes, there's gravity. And then if you go through every single question besides the force of gravity, the answer to all those are no. There's no rope, there's no spring, no one's touching it, it's not sliding or being kept from sliding, and it's not up against a surface. So again, the only force is the force of gravity. Both of these objects are in free fall, and if we remember from our videos, to be in free fall, the only force that must be experienced is the force of gravity. So these free body diagrams check out with my qualifications for free fall. But let's look at 2 and 10. A little bit different. So we've got carts being pulled by a rope, and then these carts are moving different directions. But again, the direction the cart is moving does not matter. So let's ask ourselves, is it on a planet? For number 2, yes, there's force of gravity. Is it sliding? Well, you're going to notice on the back that some of these carts have wheels and some do not. The fact that this has wheels means we're ignoring friction. So there is no friction for this cart. For applied force, is someone physically touching it? You may think so because there's a human pulling it, but the human's hands are not actually in contact with the cart. So there's no applied force. Are there springs in this problem? No. Is there a rope or string? Yes. So now the question is, which way does that string pull? Well, this rope or string is pulling to the right with a tension force. So we've gone through 5 of our forces. The last one, is it pushed up against the surface? Well, the cart is actually on the ground, which is the same deal as my coffee cup. If it's touching the ground must exert a normal force up. Just now realizing, technically, we could say that both of those are example E, and then we just drew H in this box. So if you want to write the letter, you can. Just know that the diagram you draw has to match one of these 9 up top, and that matches H. Let's talk about number 10. There's the force of gravity because it's on the planet. There's no friction because I have wheels. The human's not touching it itself. There's no spring. There is a rope, so there is a tension force pulling to the right. And then it is in contact with the ground, so there is a normal force. So this is where it gets a little tricky. Yes, these carts are moving 2 different ways. One's moving right, one's moving left. But the free body diagram is the same. The forces acting on the carts are the same. we'll talk about when we actually solve problems that the effect on this card is different depending on which way it's moving. But for my free body diagram, it makes no difference. I'm only looking at forces, not direction of motion. All right, for interest of time, I'm about to do some movie magic. In a second, you'll see all the answers pop up here. The one thing I will say first is number 14 should not have wheels. So let's just take those wheels off and pretend that's the box being held straight up against the wall. So I'll put no wheels. That means there will be some friction. All right, so here are all the answers to these. If you have questions about these, please ask. Here are all your answers.